Okay, good morning. Welcome to Geometry Project number 9. This is section 1.9, Petal Triangles, and the last two lectures, 7 and 8, have been a little intense, a little complicated. I'm going to try to keep things very simple today, and maybe even a little shorter than usual. So section 1.9 of Geometry Revisited is about petal triangles. And petal triangles are a general case of a couple things that we've already studied. But a petal triangle is, you pick any point P, could be inside the interior, could be outside of the triangle, except it turns out you get a problem if you pick P, you just happen to pick P on the Circum Circle. But for now let's look at a point P inside the triangle. And you draw the perpendiculars to the three sides. So here I've picked this point P, I've drawn P going down to side BC, perpendicular. P going perpendicular to side AC, P going perpendicular to side AB, and I've connected those 3 points, A1, B1, and C1, and that triangle is called the petal triangle, and point P is called the petal point. So the triangle that you get, the medial triangle is an example of something like this, the orthic triangle is an example of something like this. We studied those two in detail. Now we just want to see if there's anything you can say in general. Mathematicians sort of like to do this. The one thing we can say in general, there's actually two neat things proven in this chapter. I'm going to prove in the easy one, and then I'll just sort of sketch the hard one, because the hard one is just chasing angles, and you don't need to see me do that. You can go through it yourself. So what can we say about this triangle? Well, let's look at this distance here from A to P. And you'll notice that we form two triangles. If we draw AP here, I may as well actually draw it instead of drawing with dashes. I have triangle AC1P and triangle AB1P are right triangles. I'll stop drawing in green because it might be hard to see on the camera. Triangle AC1P and AB1P are right triangles. That's by definition, because we said P going to C1 is a right angle. That's how we define this triangle. And P going to B1 is a right angle. That's how we define the triangle. And that means that the AP is a diameter of the Circum Circle of triangle AC1P and triangle AB1P. And the reason that's the case is because we have this right angle at BP1A, we have a right angle at B1. So when I draw the Circum Circle, AP is a diameter. Also, exact same thing here, it's a right angle, so AP is a diameter. But that means the Circum Circle, that circle goes through C1, B1, and P. So the Circum Circle of AC1P and AB1P actually is the Circum Circle of a few other triangles. Gotta go big dot theory to make that drawing look right. Okay, so it turns out that Circum Circle is also the Circum Circle of triangle B1PC1, and that's because that circle goes through those points C1, B1, and P. So what can we say now? That this is the important thing that the book sort of skipped over very quickly, and it might have been hard to recognize why something they said was true. Okay, so what does that mean? What does that mean? So let's look at the triangle. Actually, first we're going to look at the triangle AC1B1. And we know from our extended law of sines that B1C1 over sine A equals 2 times the radius of the circumscribed circle. So A1, C1, B1, 2 times the radius of the circumscribed circle. Well, that just happens to be AP. Well, that's nice to know. Well, but we also happen to know from our original triangle, AB, that side A over sine A equals 2 times the radius of the big circumscribed circle, the circumscribed circle of triangle ABC. Well, that tells me I can say that B1C1 over AP, which is just sine A, equals A over 2R. That's just isolating sine A in each of these expressions and setting the two sides equal to each other. And so I've just learned a formula for the length of one of the sides. This tells me that B1C1 equals the side AP times side length of the big triangle A over 2 times the big circumcircle. Well, what is AP? AP is the distance from our petal point times A over 2R. Okay, so we derived a formula in general for the length of the sides of a petal triangle. You just pick your point, and then you learn how far away it is from each vertex, and then once you know the sides of the original triangle, and once you know the sides, you know the circumradius. Now you know the distance, or now you know the sides of the petal triangle. So it's a clever little formula. It's not that complicated. The reason I wanted to go through this in a little bit of detail is that they skip over this. They just go through this very quickly in the book. They point out the easiest triangle to understand this formula is the Circum Circle, where P is the circumcenter, where the distance from the circumcenter to each one of the sides is the radius R, and that tells us when the distance from the point P to each vertex is R. So for the if P is the circumcenter, then B1 C1 equals A over 2. Because the R's cancel. So the triangle that you get by connecting the points drawn perpendicularly from the circumcenter to each side, that triangle has length A over 2, side length A over 2, B over 2, and C over 2, which is half the original triangle. And they say that sort of matter-of-factly. And at first you might say, wow, that's kind of surprising. But remember, those particular points, A1, B1, and C1, when you're talking about P being the orthocenter, those are the midpoints of each side. So that's just the medial triangle. Okay, I want to show just quickly one last thing, and then we're going to be done with Chapter 1. Let me just draw a picture, and I'll be right back. Okay, so here's my new picture. I started with a triangle ABC. I pick a petal point P, which I forgot to label. So let's just call our point P is in the center here. That's point P in the middle. And I draw the first petal triangle. I drop a perpendicular, drop a perpendicular, drop a perpendicular, and I get the triangle A1, B1, C1, and I call that the petal triangle. And from there, I just do exactly the same thing again. Inside of the first petal triangle, I drop perpendiculars to each side again. Now this is my purple triangle. So I draw on this second triangle in black, I drop a perpendicular to this side here at C2, perpendicular to that side at A2, perpendicular to that side at B2, and that's my second petal triangle. And then I do it again. Inside the second petal triangle, I drop perpendiculars, and I get this triangle A3, B3, C3. And the theorem that they show in the book is that triangle, let me write it so you can see it, triangle A3, B3, C3 is similar to triangle ABC. So the third petal triangle is similar to the fourth petal, or the original triangle. Now the proof of this theorem, and you can see why I'm not going to try to go through it here because this gets very complicated with lots of little tiny angles. And again, I think it's worth, if you want to buy Geometry Revisited and work your way through this, understanding proofs like this is very helpful to your development in mathematics. I'm not sure that watching me do it is helpful, but seeing their presentation of it and then working through it yourself is very helpful. And And it's just sort of a neat theorem. All you do is you draw this line here, and then you look at this angle, and you look at this angle, and you chase those angles around to the various triangles. So it takes you 4 or 5 minutes to understand this. They mention a very neat formula that for any n-gon, so for any n-gon, so a triangle is a 3-gon. If you draw 10 points and connect them in a, that's called a 10-gon. The nth petal, I don't even know what they call it, the nth petal n-gon is similar to the original, which is a pretty remarkable theorem. They just mention that. I think they give a reference in the book. They do suggest that you try to show for a quadrilateral that that's true, and that's probably an interesting exercise, although I admit I didn't do it. So anyway, that's all I want to talk about today in section 1.9. Very neat little section. Oh, sorry, there is one other thing. This section, if you buy the book, has problem number 2, and I think it's problem number 5. Problem number 2 and problem number 4 in this section are 2 of the most clever geometry problems you will ever see in your life. So simply stated and so difficult to work through. Anyway, those 2 problems kept me occupied for weeks back when I was in high school. Loved trying to figure them out. Fun problems, worth checking out the book for. Anyway, so that's the end of chapter 1 on triangles. Chapter 2, which I'll start tomorrow, is entitled Some Properties of Circles. Thanks for watching.